is the way we analyze interaction in this kind of high-dimensional setting. And what the key difficulty is the lack of invariance to the baseline condition. So what do I mean by that? Well, it means that inference depends on the choice of baseline condition. So if you change the baseline, if you're thinking about interactive effect, your answer can change. Okay? So here's the toy example, a 3x2 example. So there's two treatments, 3 levels. It's not 2x2, it's a little bit more complex, but it's not crazy. Okay? So A takes 3 levels, B takes 3 levels. Suppose the model for the potential outcome, like the outcome, true outcome model, is just a regression, linear regression with, when I pick the baseline condition A0, B0, suppose this is the actual model that generates the outcome. Okay? So here the star is just a dummy variable. Okay, so here's just a dummy. This is an interaction, this is another interaction, coefficient is 2, coefficient is 3, and so on. Okay? So from this I look at and say, oh, okay, this interactive effect for this combination is larger than interactive effect for that combination because the coefficient here is 2, coefficient here is 1, so that's good. It turns out you can write the same exact model, nothing has changed. So McCartan was doing populating the potential outcomes table, but that's exactly what I had to do, and I was surprised to see another person who do the same, but it's a tedious process. And so then you can see that, so this model is exactly the same as this, except the baselines are different. Okay, I picked A0, B1. And now the conclusion is reversed. So interaction effect for this guy is now -1. The interaction for effect for that guy is stay the same. So it's the opposite. Right? And it also turns out interaction effect for A2 and B1 is 0 for this second model, but 3 here. Right? So as you know, like, if at least one of the treatment has the same value as the baseline value, there's no interaction in the conventional framework. So you always get zeros. Right? But that interaction effect pops out when you change the baseline. Okay, so all interaction effects with at least one baseline value are 0. Right? So this is problematic depending on the situation you're in, especially when you don't have a strong motivation for the baseline condition. Like in the conjoint, like should Somalians be the baseline, or should people from Sudan should be the baseline? It's unclear. All right. So what we do in the paper that I circulated, which is written for the technical audience, but I want to sort of convey the main results here, is that first we're going to show formally. I mean, this is just a toy example. Formally show that the standard sort of chemical interaction effects suffer from this invariance. So the lack of order, right? So if you change the baseline, the order of the effects can change. Interval invariance means the difference between those two effects can change. And so that's really problematic. And we're going to propose a new interaction effect called the marginal treatment interaction effect that is invariant to this choice. So depending on the whatever the baseline condition you pick, the relative magnitude of these interaction effects doesn't change at all. Okay? And we derive the identification condition. And it turns out it's very simple to estimate. And then the bulk of the paper, which you see, it's a lot of notations, but it basically generalizes these results to any interaction of any order. So we start out with a two-way interaction, and then go to three-way, any general higher order interaction. And it also turns out that beyond two-way interaction, the conditional effect interpretation makes very little sense. Okay, and you see why that's the case. And then we'll illustrate the methods with the immigration survey experiment. So what I'm probably going to try to do, unless if anyone has a question at this point, any questions or? Okay, so I'll just go through the two-way case to give you sort of intuition, and then I'll go to the application. to see like how the method performs with this particular data set. Okay, so let's think about two-way causal interaction. So here it's a little bit more general, so you have two treatments but any number of levels. Okay, so it goes from the dA, this of A number of levels, this of B number of levels. We're gonna assume the 4 factorial design. So our method works if we assume 4 factorial design. So what do I mean by that? Well, first we're gonna assume that the treatment assignment is randomized. Okay? But importantly, there's for any treatment combination, there's non-zero probability of assigning that particular combination. Okay, so we're not discarding some combinations. Okay, and this assumption is critical. That doesn't mean that in the realization you may have empty cells in realization, right? If you have 1 million combinations and you only got 1,400 observations, you're going to have lots of empty cells, like a lot of empty cells. But we're saying that the probability of having any observation in that each cell is not 0. Just happen to your random sample happen to have that feature. Okay. Now you might think, in some cases there may be substantive reasons to restrict these treatment combinations. So if you're a faculty member, you probably have PhD, although I have a friend who doesn't have even BA. Right, so but you could imagine that restricting potential outcomes in that way. So that's called, in the literature, fractional factorial design. So if you have missing cells, that's called the fractional factorial design, but it's not allowed in our framework. So there's